Now let us see the given statement is true or false. The first statement says that minimize the number of arithmetic operations whenever possible. So it is true, as there are several reasons why it is beneficial to minimize the number of arithmetic operations whenever possible. If first is efficiency, performing arithmetic operation is a computationally expensive process. By minimizing the number of operations required, we can improve the efficiency and reduce the processing time. Second is accuracy. Each arithmetic operations introduce a certain degree of error which can be accumulated over multiple operations. By minimizing the number of operations, we can reduce the overall error and improve the accuracy of the result. Robustness. Arithmetic operations can also lead to numerical instability and divergence, especially when dealing with large number or values. By minimizing the number of operations, we can reduce the risk of numerical instability and make the algorithm more robust. Memory uses. Each arithmetic operations requires storage space in memory. By minimizing the number of operations, we can reduce the memory uses and optimize the use of available resources. Overall, minimizing the number of arithmetic operations can lead to more efficient, accurate, and robust algorithm with lower memory requirements. Therefore, minimize the number of arithmetic operations where possible. So statement is true. Second statement states that avoid taking the difference of nearly two equal numbers whenever possible by alternate formulation of problems. If it cannot be avoided, then take the difference before doing other operations. So taking the difference of two nearly equations equal numbers can lead to the loss of accuracy and numerical instability, especially when dealing with floating point arithmetic. This is because the difference between two nearly equal numbers can result in a very small number that may be lost due to limited precision of floating point arithmetic. For example, consider the subtraction of two nearly equal numbers. So a is equals to 1.1 and b is equals to 1.2. Therefore, c is equals to a minus b. In this case, the value of c is very small and may be lost due to limited precision of floating arithmetic. This can lead in inaccurate result and numerical instability, especially if the c is used in subsequent calculation. To avoid this problem, it is recommended to use an alternative formulation of the problem that avoids taking the difference of two nearly equal numbers. This can involve algebraic manipulation or reordering of calculations to reduce the sensitivity to small changes in the output. If it is not possible to avoid taking the difference of two nearly equal numbers, it is recommended to take the difference before performing other operations. This can help to reduce the impact of loss of precision and improve the accuracy of the result. Overall, avoid taking the difference of two near equal numbers and taking the difference before performing other operations can help to improve the accuracy and numerical stability of algorithm that involve floating points arithmetic. Therefore, the given statement is true. Third statement states that adding or subtracting numbers starting with the smallest number and work with the number in ascending order. Given statement is true, as when adding or subtracting numbers with different magnitude, it is important to start with the smallest number to reduce the impact of the limited precision of floating points arithmetic. This is because small numbers have fewer digits and are less sensitive to rounding errors than a large number. By working with numbers in ascending order, we can also reduce accumulation of rounding errors and numerical instability. This is because rounding errors accumulate more rapidly when adding or subtracting large numbers, while small numbers are less sensitive to these errors. For example, consider the following calculation. A is equals to 1.23, B is equals to 0.004, C is equals to 45.67, and D is equals to 0.0005. If we add these numbers in a descending order, we get result A plus C plus B plus D, which is equal to 46.9035. However, if we add them in ascending order, we get result is equals to B plus D plus A plus C is equals to 46.9035. In this case, adding the small numbers first reduce the impact of rounding errors and improve the accuracy of the result. Overall, adding or subtracting numbers starting with the smallest number and working with the numbers in ascending order can help to improve the accuracy and numerical stability of the calculation, especially when dealing with floating point arithmetic. Therefore, the given statement is true. Now, let us read our next statement. Do not formulate an algorithm test whether a floating point number equals 0. It is not recommended to formulate an algorithm that tests whether a floating point number equals 0 because floating point numbers are not equal and their values may be subjected to rounding errors. Due to the limited precision of floating point arithmetic, it is difficult to represent certain numbers exactly, including 0. This means that even if two floating point numbers are mathematically equal to 0, their representation in memory may differ due to rounding errors. Instead of testing whether a floating point numbers equal 0, it is better to use a threshold or tolerance value to check whether the absolute value of the number is sufficiently small. This approach is also known as Epsilon test. Here is an example of Epsilon test algorithm in pseudocode. Function is 0, x comma epsilon and return abs x where epsilon is greater than abs x. In this algorithm, x is a floating point number being tested and epsilon is the tolerance value. The abs function is used to get the absolute value of x and the function returns true if the absolute value is less than epsilon, indicating that x is efficiently 0. Using an epsilon test, we can handle floating point number more accurately and robustly than testing for exact equality to 0. In the fifth statement, conditioning of problem is normally due to improper formulation and can be eliminated carefully by reformulating the problem. A practical way, if detected suspected ill conditioning, is to alter the parameters by small amount and observe their effect on the solution. Partially true. The statement is partially true. Ill conditioning of problems can be due to improper formulation, but it can also be due to the nature of the problem itself. Ill conditioning means that small changes in the input or parameters of the problem can lead to large changes in the output or solution. This makes the problem difficult to solve accurately and can lead to numerical instability. One way to detect suspected ill conditioning is indeed to alter the parameters by small amount and observe their effect on the solution. This is known as sensitive analysis. By analyzing the sensitivity of the solution to change in the input parameters, we can determine the problem is well conditioned or ill conditioned. If the solution is highly sensitive to small changes in the input, then the problem is likely to be ill conditioned. However, simply altering the parameters of the small amount may not always be enough to eliminate ill conditioning in some cases. A careful reformulation of problem may be necessary to improve its conditioning. This may involve changing the formulation of the problem, introducing additional constraint or assumption, or using a different numerical methods or algorithm. Therefore, while detecting suspected ill conditioning through sensitivity analysis is useful first step, addressing ill conditioning may require a more thorough analysis and reformulation of the problem. The sixth statement states after a numerical algorithm is obtained, check if it can lead to numerical instability. In such algorithms, error goes in each steps of calculation. In such case, reformulate a solution procedure to get a stable numerical algorithm. This statement is partially true, as numerical algorithm can indeed lead to numerical instability, where error goes in each steps of calculation. This can be due to variety of factors such as ill-conditioned problem, numerical round of errors, or instability in algorithm itself. To ensure numerical stability, it is important to carefully analyze the algorithm and its implementation to identify potential source of instability. This may involve testing the algorithm on a range of input values. Examining the behavior of algorithm as input values are varied and comparing the result with analytical or exact solutions where possible. If numerical instability is detected, then the solution procedure may need to be reformulated to get a stable numerical algorithm. This may involve using alternative numerical methods or algorithms that are known to be more stable. Modifying the existing algorithm to reduce the impact of numerical errors or round off, or introducing the additional constraints or assumption to improve the conditioning of the problem. Therefore, while checking for numerical instability is an important step in the development of numerical algorithm, addressing instability may require a more thorough analysis and reformulation of the algorithm to ensure that it's stable and reliable for a range of input values and conditions. The seventh statement states if severe rounding errors and consequent loss of significant digit is anticipated and if no alternate formulation to avoid this is possible, then carry more significant digits in a critical calculation using floating point numbers in double precision mode. In this mode, the length of the mantissa is twice that of other floating point quantities. Statement is true, as severe rounding errors and consequent loss of significant digits can occur in numerical calculation, particularly when dealing with quantities that vary widely in magnitude or when performing operations on values that are close to the limits of machine precision. In such cases, if no alternate formulation is possible, to avoid this loss of precision, carrying more significant digits in critical calculation can help to minimize the impact of rounding errors. One way to achieve this is by using floating point numbers in double precision mode, which allows for twice the number of digits in mantissa compared to standard floating point number. This can help increase the precision of critical calculation and reduce the potential for rounding errors to affect the accuracy of the final result. However, it is important to note that increasing the precision of the calculation can also increase the computational cost and memory requirements of the algorithm. Therefore, it is important to carefully balance the need of the precision against the computational resources available and to consider alternative methods or formulation where possible to reduce the impact of rounding errors on the final result. Double precision requires large memory and slow down calculation. This is true, as double precision requires more memory space than standard single precision, as each double precision floating point number requires 64 bits of memory compared to 32 bits for a single precision number. However, whether or not double precision slow down the calculation depends on the specific context and computational requirements of the algorithm. In some cases, double precision may be necessary to achieve the desired level of accuracy or to avoid numerical instability caused by rounding errors. In this situation, the benefit of increased precision may outweigh the additional memory requirements and computational cost. In the other cases, where lower precision is sufficient or where the computational resources available are limited, it may be more efficient to use single precision floating point number or to consider alternative methods or formulation that reduce the impact of rounding errors on the final result. Ultimately, the choice precision for a numerical algorithm should be based on careful consideration of the trade-off between accuracy, computational efficiency, and memory requirements, taking into account the specific context and goals of the problem being solved. In the third iteration of the finding square root of 5 with standard 0.7 using Newton-Raphson method, relative error is 0.0013. So, based on the given information, we can make an assumption that the formula used to find the square root of 5 is xn plus 1 is equal to 0.5 xn plus 5 by xn, where xn is the nth approximation and x comma n plus 1 is the n plus 1 approximation. We can estimate the value of x3 third iteration as follows. So, x0 is equal to 7, x1 is equal to 0.5 into 7 plus 5 by 7, which is equal to 3.07143, and x2 is equal to 0.5 into 3.07143 plus 5 by 3.07143, which is equal to 2.23868. Now assuming that the relative error is defined as as xn plus 1 minus xn by xn plus 1. We can calculate the relative error between x2 and x3. Relative error is equal to x3 minus x2, which is equal to 0.0013. So therefore, the third approximation of square root of 5 using a Newton-Raphson method with starting point 7 and relative error of the approximation is 0.003 is approximately 2.244119. The iterative methods are compared on the following parameters: the rate of conversion, the amount of computational efforts per iteration, sensitivity of the methods to starting value and intermediate value. Yes, rate of conversion refers to how quickly the iterative method converges to the desired solution. The faster the rate of convergence, the better the method. Amount of computational efforts per iteration. It refers to the amount of computation required to obtain the next approximation in the iterative process. A method that requires less computational efforts per iteration is performed. Therefore, the given statement is true.